That's right. So the HA is for Haagerup, and it's supposed to look like ordinals. So it's also, there's a property, so the Haagerup property is property H, I'll discuss, and then there's a generalization, which is due to Ozawa. He called it property HH, or haha, and then Monod decided to name a property ha ha ha, so I thought I would go ha 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 ha. Okay, so thank you very much for the opportunity to speak here. I should mention this is joint with my student, Fabian Salinas. So I know that many people in this room are not operator algebraists by trade. So I thought I would be a little bit gentle with this talk and give more of an overview of the results without actually discussing a lot of the details. But so I want to start with going all the way back to the work of Murray and von Neumann from the 40s. So what did they do? Von Neumann. So they introduced group von Neumann algebras. So they start with a group, gamma group, and then you can consider the left regular representation of the group. So lambda, this is mapping the group to the unitary group on L2 of the group itself by just extending the multiplication onto the basis elements. And then they define the group von Neumann algebra to be the, so you can take the span of this, the complex span of the range of this, and then this is a star algebra inside of B of L2, and you can take its SOT closure, strong operator topology, or you can consider this as left convolution operators, as Ben introduced it in his talk. And this is the group von Neumann algebra. So this is some von Neumann subalgebra of bounded operators on L2 of gamma. And so they were very interested in this class of von Neumann algebras. One of the reasons that they were particularly interested in this class is because these are finite von Neumann algebras. You have a canonical trace. So this is a trace, and it's given by tau of an operator as just you take the vector state corresponding to the Dirac function at the identity. And this is, it's a vector state, so it's a state, but it also satisfies this nice trace property that the trace of xy is equal to the trace of yx. They also noticed, so that in the case when gamma's ICC, so gamma has infinite non-trivial conjugacy classes, which they abbreviated ICC, if and only if the center of the group von Neumann algebra is as small as possible. So it's just the scalars. And they knew that somehow factors were the building blocks of von Neumann algebras in general, so they were interested in studying this. So we have finite factors. So this, these are 2-1 factors if you have an infinite ICC group. And they were interested in this. In particular, they were, you could consider when gamma is the symmetric group, the group of finite permutations on the natural numbers. So this is an ICC infinite group. So this gives a 2-1 factor. This is the hyperfinite 2-1 factor, usually denoted by R, the hyperfinite factor. And this was a particularly nice example of a 2-1 factor that they were interested in. And then another example, which they also considered, was a free group on 2 generators. So this is a free group factor. And one of the results in their paper from 1945 is, in fact, that these 2-1 factors are not isomorphic. So we have R is not isomorphic to LF2. And the way they distinguish them is by what a property they called property gamma. So R, the hyperfinite two-one factor, has property gamma, meaning that there are sequences in R that asymptotically commute with everything. And then they had an argument showing that for free group factors, this did not hold. So they considered a number of other factors, another number of other groups. So like another group they considered was the group von Neumann algebra. You take the direct product of these two. But they even mention in their paper that they're unable to distinguish this factor from R, because in fact this factor also has property gamma, and that was the only invariant they had at the time of distinguishing two-one factors. They also, one thing which struck their interest is they did notice, however, they consider not just isomorphisms of, say, two-one factors, they also considered embeddings of two-one factors. And one of the things they did is they constructed, ICC groups, say gamma 1, gamma 2, such that their von Neumann algebras were not isomorphic, but because one had property gamma and the other didn't, but L gamma 1 did embed into L gamma 2, and L gamma 2 embedded into L gamma 1. So they were really interested in what types of embeddings, like even if you can't say, even if you don't have isomorphic, maybe you have embeddings. But again, so the one that had property gamma, they couldn't distinguish it from R. The one that didn't, they couldn't distinguish it from LF2, because those were the invariants they had. And so in particular, at the time, they didn't know, could LF2 embed into R? Could this group embed this group embed into LF2? These were all natural questions that they might have considered, and they just did not have the tools to answer. Well, shortly after the work of Murray and von Neumann, some tools were developed to handle this case. This was due to Jacob Schwartz, who showed that, in fact, L of S infinity times F2 is not isomorphic to LS infinity, even though they both have property gamma of Murray von Neumann. And how he did it is he used the fact that this group right here, so R, has a nice approximation property. So specifically, R, because S infinity is a locally finite group, and so you can write this von Neumann algebra as a union of finite dimensional von Neumann subalgebras. And so if you have R, so R, you have this, inside of R, you have all of these n by n matrices. So they naturally embed into R, and you take their union and you get something dense. And so this means with R, it has this nice property that you can take the conditional expectation onto these n by n matrices to get down to the n by n matrices. And then you can just embed them back into R. And when you take the compositions, so this is embedding, and when you take the composition of these two things, you'll get some sequence or net of completely positive maps. So conditional expectation and inclusion are both completely positive. So these are completely positive maps. Their range is finite dimensional because it factors through this matrix algebra. And yet they converge to the identity, say in the strong operator topology as n goes to infinity. SOT, and this is for all xn. So this is a nice property that the R has. This is called semi-discreetness, and is a very nice approximation property for the hyperfinite two-one factor. A result of con is that the converse, in fact, also happens, that if you're a two-one factor semi-discrete, then in fact you're isomorphic to R. That's a much deeper result. But what Schwartz was able to show is that, so of course this approximation property, it's easy to see it passes to all subalgebras. And Schwartz is able to show that if if L of gamma has or is semi-discrete, so then gamma is amenable. So that's what he was able to show. So in particular, if you did have an isomorphism or even an embedding of this group von Neumann algebra into this, then you would get that this group is amenable, but it's not amenable because it has a copy of a free group inside. So this is the argument there. So in fact, his same argument shows that you don't have even an embedding here. So this is interesting. You might also ask, well, what about embedding into LF2? Well, you clearly have an embedding of LF2 here. And as I just explained, you don't have an embedding here. But you could ask, does L of S infinity times F2 embed into LF2? So that's the next natural question stemming from Murray and von Neumann's work. It turns out it took quite a bit longer to show that this is not possible. So the answer, so this is the question, and the answer is no. And this was shown by Ozawa in 2004. So it took quite a bit of time to eventually show that this embedding is not even possible. Shortly after Ozawa proved this result, there was a result of Soren Popa and myself separately, independently in 2006, where we gave another proof of this fact that there's no such embedding of this von Neumann algebra in here, or more generally, Ozawa showed that free group factors are what he called solid, so that you don't even have any embedding of any sort like this in here. So I just wanted to mention that. So at the time, so we had these proofs, so I want to just mention also now with free entropy and these very nice results on strong convergence and everything. So this gives a new proof of this fact, and this is one of the reasons why, to help with some context, this was kind of the starting point for why I wondered about these sorts of maximal injective things and free group factors. Was starting from this. So it's very nice that we now have a proof from free probability and random matrices that this also can happen. All right, but now there's another way, there's another approximation property that you can try to generalize maybe from R. And this was noticed by Haagerup. This is Haagerup.
So should it be obvious to us why that result implies this one?
Yeah, because if you look at, well, I mean, I shouldn't say something should be obvious, but it's not difficult. If you look at this von Neumann algebra, so say F2 is generated by A and B. If you look at this von Neumann algebra, this is amenable. Or you could also look at this von Neumann algebra. This is also amenable. And their intersection contains S infinity, which is diffuse. So therefore, by this unique injective, maximal injective thing, you would get a contradiction. Yeah. So, and many more things. In fact, even if you just had an action of F2 on S infinity, you could do this. But this was done earlier by Ozawa and Popa to show that even if you had an action here, you wouldn't embed. Okay.
And the other minor question I have, which I missed, is does L of S infinity embed in L of F2?
Yes, in fact, that already follows from the work of Murray and von Neumann. They showed that, in fact, L of S infinity embeds into any 2-1 factor. Yeah, I should have mentioned that. Thank you. So now I want to go to the work of Haagerup from the late 70s, 79, where he considered another approximation property. So we know that LF2 is not semi-discrete. It doesn't have this. However, what he showed is, in fact, it has a slightly, if you modify it slightly, you do have an approximation property. So he showed that there exists a sequence of unidal completely positive maps on LF2 that even preserve the trace, such that while they still have an approximation, so you still have theta n of x minus x goes to 0 SOT for x and LF2. And they're not so far away from being finite rank. What you have to replace finite rank with is that if you look at the uniball and LF2, you just ask that this is always SOT compact, or maybe take the closure in the SOT, is compact, SOT. So the image of the uniball is compact in the strong operator topology. Of course, semi-discreetness, you get this for free because the image is contained in the image of the uniball here, which is finite dimensional, so you're good. But he showed, in fact, you can get away with a slightly weaker property. And this can be rephrased in terms of the group. In fact, so the way he did this is by showing that the word length function on the group is conditionally negative definite, and then you construct these UCP maps from this fact. And so in general, the consequence you get, so let me give you a definition. This is the Haagerup property. So the definition is that gamma has the Haagerup property which I'll just denote by property H, if there exists a representation, a unitary representation of your group, and U of H, such that it weakly contains the trivial representation. So this has almost invariant vectors. But that the coefficients decay very fast, specifically that the coefficients, so if you look at the function from T to your group and you look at the corresponding matrix coefficients for this representation, these should vanish at infinity. So these are all in C0 of the group, and this is for each Xi and eta in your Hilbert space. Yeah.
Was our original representation that was previously on the board, was that the regular representation?
Correct. That was the left regular representation. This now is just any representation, but you want to satisfy this property. So this is called a mixing representation. And of course, as you might notice, the left regular representation is a mixing representation. And so if the left regular representation weakly contains the trivial representation, then you have the Haagerup property, and that's exactly amenability. So amenability implies the Haagerup property. And from this property here, you can construct, this allows you to construct these maps from the group von Neumann algebra into itself, these UCP compact maps that Haagerup did. So in general, whenever you have this property, the von Neumann algebra has this corresponding Haagerup approximation property, and conversely, this is a result of Choda. Moreover, because this is a natural approximation property, this approximation property also passes to any subalgebra. While there's a natural kind of extreme opposite of the Haagerup property, and that's property T. So gamma has T if, now for any representation, any unitary representation pi, so if pi has almost invariant vectors, that is, it weakly contains the trivial representation, then it's only for the obvious reasons that it actually has invariant vectors, so it contains the trivial representation. So this is property T. And of course, from this definition, you see, well, if it contains the trivial representation, then the constant 1 function has to be C0. So if you're mixing and if you have the Haagerup property and you have property T, then that means the constant 1 function is C0, so you must be a finite group. So that's the remark. So the remark is that if gamma is infinite and has T. So property T was introduced by Kazhdan. I should give you some examples. So Kazhdan proved that SL and Z for n, actually Kazhdan proved it for n greater than or equal to 5, I think, but it's since been n greater than or equal to 3. You have property T. And so we know that these group von Neumann algebras, so I guess they're not ICC, but if we make them ICC, these group von Neumann algebras don't embed into, say, a free group factor. Right, that's another consequence of this approximation property. In fact, you can do a bit more with this. Let's see. There's the clock. You can do a bit more with this. And you could introduce the notion of relative property T. So yeah, I'll rewrite it as a new definition. So then this is a remark, if this is infinite, n has T, so then gamma is finite. So therefore, as an example, if gamma is equal to this, then L gamma does not embed into L lambda if lambda has H.
This is finite.
Then and has T, then, oh, yes.
Did you say does not embed?
So then, all right, forgetting all my negations.
You said if gamma is infinite and has T. Has both H and T.
F has H and has T. I think it's now correct. All right. I got a thumbs up from Ben, so I know I'm good. Okay, so this is a nice consequence. So this gives you an obstruction to embedding property T groups into a von Neumann algebra. The Haagerup property is an obstruction, and in fact, there's even a better obstruction. The Haagerup property gives you even a better obstruction, and that's to relative property T. So now, if we have a subgroup, so then the pair sigma gamma has relative property T if it's a similar thing. So we, whenever we have a representation pi, a rep, so this is a unitary representation, then we have the implication that if the trivial representation is weakly contained in pi, so if we have almost invariant vectors, then that means we do have invariant vectors, but not for the whole group, but for the subgroup. Yeah, I see a hand.
I was going to ask if pi is a representation of gamma.
Yeah, pi is a representation of gamma. I was trying to save time by not writing it out. But. So this is relative property T. This was introduced by Margulis, for instance, and the natural example here is if we take Z2 cross SL2Z with its natural action, and we take the subgroup Z squared, then this has relative T. Well, the same argument I gave you showing that property T groups don't embed into the von Neumann algebra of Haagerup groups work just as well if you have an infinite subgroup with relative property T. So that's another remark, is that if gamma has an infinite subgroup, sigma, such that the pair gamma sigma has relative T, so then L gamma cannot embed into L lambda if lambda has the Haagerup property. So this is another obstruction to embedding into groups with the Haagerup property. So for instance, this group. And this group played a key role in Poppa's development to deformation rigidity, and specifically the fact that Z2 has relative property T, but SL2Z itself has the Haagerup property. So this juxtaposition, this struggle between property T and the Haagerup property was really the beginning of deformation rigidity theory. But in some sense, you look at this example, and I mentioned this, this is a group. It doesn't have the Haagerup property because you have this infinite subgroup with relative property T, but somehow it seems to just barely not have the Haagerup property, in the sense that it is an extension of an amenable group with a group with the Haagerup property, so it shouldn't be so far away from having the Haagerup property. So what I want to do now is discuss how you can actually formalize this notion. How can we say that this group, is, barely non-Haagerup? So I'm going to introduce a new approximation property. So let me see exactly how I want to introduce this. So let me explain what I mean by this group barely doesn't have the Haagerup property. So let's consider this group. So now, given a group, given gamma, let's define. So Haagerup property says the trivial representation is weakly contained in a mixing one. So let's look at this, say, universal mixing representation. So let's define pi sub mix. This is going to be, say, the direct sum of all representations such that pi is mixing. And what you can check is, of course, taking direct sums preserves mixing. So this itself is a mixing representation and contains everything. Don't worry about the set theory thing. It's just restrict yourself to Hilbert space of large dimension. So another way to say the Haagerup property is that the trivial representation is weakly contained in this particular representation. So if we don't have the Haagerup property, then what we can do is we can define whatever representation is the universal one that's weakly contained in this representation. So we'll define, say, or pi mix, say, weak. So this is going to be the direct sum now of all representations of pi, such that pi is weakly contained in this mixing representation. So another way to say the Haagerup property is that gamma has H if and only if the trivial representation is a sub-representation of this one. Okay, so far we haven't done anything. But this means in particular, if you don't have property H, like this group here, so then this gives you some representation. It doesn't have invariant vectors. So what you can do is you can look at the coefficients of this representation and just decide, okay, well, these coefficients are supported on small sets. So let's now define the following thing.
Can I ask you a question?
Yes.
Pi mix is a direct sum of irreducible representation?
No, just all unitary representations.
We sound self-referential, right? Because pi mix is mixing.
So the difference is, so I was trying to avoid set theory. Say on Hilbert spaces, spaces of dimension at most the cardinality of gamma. Now it's not self-referential. And then you do the same thing here, right? Or maybe cardinal is some larger cardinality. Okay. So now what we can do is we can take this, assign a universal representation that's weakly contained in mixing representations, and we'll just look at the coefficients of this. So we'll look at these functions. And we'll just decide that these functions are in some sense C0. We'll decide that these are small functions. And somehow. So we'll look at this. So now the definition. So definition. So let's call this phi xi eta. So the definition is that a set X inside of gamma is small. I'll I'll just leave it without quotes. If there exists some constant greater than 0, and there exists some C and H in this Hilbert space corresponding to this representation, such that these coefficients, such that X is contained in the set of T and gamma, such that phi C eta of T in absolute value is greater than or equal to C. So we'll decide that these are small sets somehow. So if you have the Haagerup property, then that's saying the whole group is small, right? And that's somehow measuring the approximation property. But for instance, this example here, well, what do we know? Well, Z is amenable. Z squared here is amenable. So that means that the trivial representation of Z is weakly contained in the left regular representation here. And so what that means is that the quasi-regular representation, so the representation coming from SL2Z, is weakly contained in the left regular representation. So let me give you an example here. So this is for gamma to be SL2Z squared cross SL2Z. So then what do we have? We have that the representation, so the left regular representation mapping gamma, but not to the left regular representation itself, but the one factoring through L2 of SL2Z. So if we quotient out by Z, this representation is weakly contained in the left regular representation of this group, which is mixing. So that means the coefficients of this representation give you small sets. So as a consequence of this, we get that therefore this set Z squared, or even any finite cosets, finite union of cosets of this, is small. So we've somehow quantified how far away we are from the Haagerup property itself. We see that these sets are small. But now what you can do is you can then say, well, now let's look at mixing representations of SL2Z. Mixing representations of SL2Z have the property that their coefficients, functions, are small, that they vanish here. So we'll say now that a representation pi is, say, I don't want to say mixing anymore, but I'll say one mixing. So it's one step away from mixing. If for all C greater than 0, for all C and eta and H, the set of T and gamma, such that these corresponding functions, T in absolute value are greater than equal to C, is small. And so if we look at any mixing representation of SL2Z and view it as a representation of gamma, we get that it's one mixing, one step away from being mixing. And since SL2Z has the Haagerup property, the consequence we get, so here's now the definition. We'll say that gamma has H1 if there exists a one mixing representation such that it pi, such that it weakly has almost invariant vectors. Of course, if there's a mixing representation, it's one mixing, so we get, so note that property H implies property H1. So H, which I'll think of as H0, it's the zero steps away from the Haagerup property. So this implies property H1, but we've seen also here, so SL2Z, or Z squared cross SL2Z, has H1. So here's an example where you're one step away. So this is again an approximation property, and maybe it's not obvious, but it turns out it can be encoded by the group von Neumann algebra. So that's maybe the first theorem I'll list. So the theorem is that if we have L gamma is isomorphic, or even if, of course, it passes the subalgebra, so even if you embed into L lambda. And lambda has H1, so then gamma has H1. So in particular, if they're isomorphic, one has this property if and only if the other one does.
One thing which I'm a bit ignorant of right now, I'm pretty sure I know what it means for the trivial representation to be weakly contained in something else. What does it mean for two arbitrary representations?
Okay, so what I mean to say is that the matrix coefficients, when I write, when I said here, I mean that every matrix coefficient of pi can be approximated by matrix coefficients of this representation. Okay. So this is the consequence we get. So in particular, this gives a new invariant. And then you can also, and it passes the subalgebra, so it's a new approximation property, a new way to show that you can't embed one von Neumann algebra into it. And then, of course, if you can do something once, you can do it infinitely often. So that's the next step. So in general, so we can define, say, pi mixing 1 to be the direct sum of all representations pi, such that pi is 1 mixing. We can define pi mixing 1 weak to be the direct sum of all pi, such that pi is weakly contained. And this. And then we can define, now we can define step 2 small sets as those sets coming from coefficient functions here. And that allows you to define 2 mixing representations. And now you can define property H2 as there exists a 2 mixing representation such that it weakly contains the trivial representation. And of course, we can go again and again and again. And then for limit ordinals, you could take unions of small sets to define their small sets. And so in fact, you can define this for any ordinal. So in this way, we define property H alpha for any ordinal alpha. And then you have, of course, property H alpha implies property H beta if alpha is less than or equal to beta. So these give you weaker and weaker still approximation properties. However, you still, and in particular, they all pass to von Neumann subalgebras. They all pass to von Neumann subalgebras. In particular, they're all invariants of the group von Neumann algebra. Each property H alpha is itself an invariant. So each property H alpha can be encoded by the group von Neumann algebra. So in fact, we get a whole ordinal. So the one thing I haven't shown you is I've shown you examples of the Haagerup group. I've shown you examples of H1. I should also mention property T groups don't embed into any of these. But I haven't shown you examples of H2 or higher 3 or 4. And they turn out to be a bit more difficult to construct. However, it's possible. So I'll write the proposition is that for each countable ordinal, alpha, there exists a group with property H alpha, but without property H beta for beta less than alpha. So for each countable ordinal, so this is countable, there's a countable group. You can even take it to be 3 generated if you want. there exists a countable group with property H alpha, but it doesn't have any of these weaker approximation properties. However, by a simple cardinality argument, you could also argue that, so if M is a separable to one factor, so then there exists a countable ordinal, alpha, such that if L gamma embeds into M and gamma has H beta for some beta, so then gamma has H alpha. So you get this upper bound on approximation properties which embed. So as a corollary, I'll end here, is that you get a new proof of Ozawa's result, which was also from 2000, maybe 4 or 6, somewhere around there, early 2000s, so that there does not exist a separable universal to one factor, meaning it contains isomorphic copies of every other separable to one factors. So in fact, this gives you an upper bound on which of these groups can embed in it. So the one final remark I'll make is that Ozawa did this using property T also. Here, in fact, our von Neumann algebras property T can't even embed into them. We have relative property T, which is still some rigidity, but none of our factors even contain a property T subalgebra. All right, so I'll stop there. Thank you for